Solid Phase Peptide Synthesis, or SPPS, is a stepwise method for constructing peptides directly on an insoluble support. The process begins with anchoring the first amino acid to resin through a special linker. Then, the peptide chain is extended one amino acid at a time through repeated cycles of deprotection and coupling, until the desired sequence is complete. Finally, the peptide is cleaved from the resin, side chain protections are removed, and the crude peptide is purified. Each of these stages relies on specific reagents, and the choices we make for each reagent determines how efficient and clean the synthesis will be. This video will provide an overview of the key reagent options available for peptide synthesis, including those for resins, linkers, deprotection reagents, coupling reagents, side chain protecting groups, and cleavage solutions. In SPPS, the amino group of the amino acid being added is initially protected or blocked for better reaction control. This prevents unwanted side reactions and ensures amino acids are added one at a time in the correct order. Historically, peptide synthesis relied on the Bach strategy, which uses acid-labile protecting groups. Bach chemistry is robust, but deprotection requires strong acids such as TFA or even hydrogen fluoride, which are harsh and hazardous to handle. Contrast, the FMOC strategy uses a base labile protecting group, most commonly removed with piperidine. FMOC chemistry is gentler, orthogonal to acid-sensitive side chain groups, and highly compatible with automation. That's why today, nearly all modern peptide synthesis is carried out using the FMOC approach. Moving forward in this video, please assume all reagent options discussed are those compatible with the FMOC SPPS strategy. SPPS resin beads are insoluble solid supports that anchor a growing peptide chain. A resin's core is typically polyethylene glycol, PEG, polystyrene, PS, or a combination of the two, PEG, PS. Different resin cores have different swelling properties. Low-swelling PS resins are a good candidate for simple peptide sequences, while higher-swelling PEG and PEG-PS resins are ideal for longer peptide sequences. Consideration of swelling is important for optimizing peptide yield and reducing issues resulting from steric hindrance between growing peptide chains. Another important resin property is substitution, or the density of peptide anchor points, which is typically measured in millimole per gram. It indicates the loading capacity of the resin, or how many peptide chains can be synthesized per gram of resin. Like swelling, substitution is important for optimizing yield and mitigating steric hindrance. For lengthier and/or bulkier sequences, a high-swelling and low-loading resin is always recommended. This information is disclosed by all commercial resin retailers. Please note that resin beads come in many sizes, with 100 to 200 mesh being most common. It is important to check resin mesh size compatibility with the manufacturer of your specific SPPS reaction vessels. Linkers are chemical spacers that connect the first amino acid to the resin core and determine how the peptides will be released, or cleaved, at the end of the synthesis. They play a crucial role in defining the C-terminal functional group of the final peptide, such as a carboxylic acid or amide. Common linkers include the Wang linker, which yields a free acid, and the Rink amide linker, which produces a C-terminal amide. Both linkers are widely used for their stability and predictable cleavage properties. For commercially available resins, linkers are nearly always already attached to the resin core. Both the Wang linker and Rink amide linker require a concentrated TFA solution for cleavage. This treatment, aside from releasing the peptide from the resin and linker, also removes any acid-labile protecting groups from the amino acid side chains. There are also specialized linkers such as CBER, 2-chlorotridyl, or HMBA, which allow selective cleavage under mild conditions or facilitate fragment-based assembly strategies. These options are powerful, but they tend to be more expensive and less universal. During each cycle, the FMOC group must be removed to expose the amine for coupling. The most common reagent is piperidine, fast, effective, and the historical standard for both manual and automated synthesis. Piperazine is a gentler alternative, which works more slowly, but may minimize side reaction risk in certain instances. Lastly, there is pyrrolidine, a strong and efficient base that provides quick and clean deprotection and is utilized in ultra-efficient synthesis methodology. If performing SPPS on an automated peptide synthesizer, we recommend you consult with your system's manufacturer for recommended solution concentrations and reaction method specifics. To form each peptide bond, the carboxyl group of the incoming amino acid must first be activated. There are two main strategies for coupling: onium salt-promoted activation and carbodiimide-promoted activation. In onium salt-promoted activation, a uronium, aminium, or phosphonium salt is used in conjunction with a base, commonly DIEA. In carbodiimide-promoted activation, a carbodiimide is used in conjunction with a coactivator, commonly oxima. While onium salt activation is the most popular choice for room temperature syntheses, carbodiimide activation is the gold standard for high temperature, high efficiency syntheses due to its high stability and ultra-low racemization risk. Once the carboxyl group of the incoming amino acid has been activated, the deprotected amine of the solid supported peptide can react with it to form the peptide bond. Like with deprotection, if you are performing SPPS on an automated peptide synthesizer, we recommend you consult with your system's manufacturer for recommended solution concentrations and reaction method specifics. While the FMOC group is used to protect the backbone amine, protecting groups must also be present on any side chain with reactivity potential. Of the 20 canonical amino acids, 12 contain functionality which must be protected. The most common protecting group used for each amino acid is displayed here and includes tert-butyl, Bach, trittyl, and PBF. Please note that for high-temperature, high-efficiency syntheses, alternative derivatives for aspartic acid and histidine are recommended. While more costly than the listed FMOC derivative, these two derivatives offer exceptional resistance to common side reactions like aspartamide formation and racemization. The final stage of SPPS is cleavage, releasing the peptide from the resin and removing the side chain protecting groups. In most cases, and always with Wang and Rink linkers, cleavage is performed with concentrated trifluoroacetic acid, or TFA, and is used in cocktails with scavengers like TIS, water, and/or DODT. These scavengers capture reactive byproducts and protect sensitive residues. This approach is highly effective, but the harshly acidic conditions can still damage particularly sensitive sequences if treated for excessive periods of time. Specialized strategies do exist utilizing milder systems such as dilute TFA or mixtures like acetic acid with TFE and DCM. These strategies, however, are reserved for specialty linkers with the purpose of cleaving the peptide from resin without removing side chain protections. This concludes this SPPS Reagents video. As a reminder, we reviewed the varying reagent options involved in peptide synthesis, including those for resins, linkers, deprotection reagents, coupling reagents, side chain protecting groups, and cleavage solutions. Thank you for your attention. Please don't hesitate to reach out to your CEM representative or synthesis.support@cem.com with any questions.